One game, yeah.
He doesn't even play F1. That's the funny part. He doesn't. He hates the F1 game. So he does like the endurance races. They're not really F1. He does like.
That's what you can talk about. His job, because if you're doing like stuff that includes your job on your side, yeah, you love your job. It's on you. You did like a affiliation of box race thing. Oh, yeah. Yeah, he didn't basically, he didn't have any issue with that. It was just now good. I thought he traded like a I like that.
Well, welcome back, folks. Looks like we're just about there. Oh, we are there. Welcome back, everyone. So we're nearly done with section 11.6, and now we're nearly done with chapter 11 as well. It's kind of amazing how it kind of culminates really fast once we get down to here. 11.8 is going to be power series. That's a big section on its own. 11.9 is going to be taking typical functions like maybe natural log x, for example, representing them as power series. But at that point, we're really doing Taylor series, Maclaurin series in a real sense. And that takes us right into 11.10. We're going to split it into really two sections because that's a pretty big one. And that's what's going to culminate in chapter 11. But really, this stuff, even though we go into power series, it's all just still on the table. For power series, we'll almost always start with the ratio test. It would be exceptional to use a root test. That'd be a weird problem. But once we use the ratio test in power series, we'll find that this represents a failure of testing, right here, right on the boundary. We have a variable x in power series, and so the test is going to be relative to what x values take. Because ratio test is inconclusive on one spot, we resolve the inconclusivity by all of these other tests go right back on the table for power series. So it's a pretty interesting concept, but the good news is we look into and start by using ratio test and root test as our very first step. So that's a great tie into what we are working on just in 11.6. I don't really have too many announcements other than we'll be pretty soon right into section 11.9, probably finishing this one when we return next week on Monday. We'll see where we end. That means 11.8 has the possibility of being the last section on the exam 3 material. And over the weekend, starting on Friday, I'll be finalizing the information here so we know the exact coverage and are able to prepare. Well, any last questions at all, folks, before we get started? Okay, here's where we left off. We are about to do this problem. But before we hit that problem, there's also a really interesting question that was posed by the class. If a series is known to converge absolutely, as is a given information, it was asked, will it also be true that the ratio test will output a limit less than 1 for the correct conclusion of absolute convergence? Answered in the class right at the very end was no. A p-series is a great example to that. A p-series can converge absolutely, but a p-series is never something you should use the ratio test on. This would give us inconclusive. So this is inconclusive. Let me try to spell that word better. Inconclusive in ratio test for, just say a really quick example, summation 1 over n squared. Yet, this converges absolutely. It's absolutely convergent because, well, it's positive. We took the absolute value of it. It's still just itself. Then it becomes a p-series with p equals 2 greater than 1 for convergence. So p-series is an immediate counterexample to this. The source on this one is anonymous by request, but that's a good tie into that last concept right before class ended. Any questions about that logic question here? Okay, it's a great question because it's also another reminder We're going to start using ratio test a lot in the very next section, but these tests will always play a really strong role throughout the entire remaining of the chapter. It's kind of interesting. So now coming down below, here's our last one to give a try on. Just like all the others, that N right there is the one part that indicates probably we should skip every single test except root test. Root test is the dead giveaway on this one. So let's say root test should be used. And it's a should. It shouldn't say must be used. If you find a creative way to analyze this and you get the right conclusions with the right steps, that's totally fine as well. But this represents the least amount of steps. Let's use the most powerful method for the problem at hand. We'll name the entire series a summation of AN. We said we're using the root test here, but let's say it more loudly. Root test means we're immediately taking a limit as n goes to infinity of the nth root of the absolute value of the nth term. That's a lot of stuff already. But all of that's the nth term. The absolute values are irrelevant on this problem because it's positive by its nature for every value of the integer n. So this is now just a limit. N goes to infinity, nth root, n plus 1 to n plus 1, power n. We chose the root test because this nth root right here is going to cancel off the most annoying part of the series. This is hard to analyze because of the n right there. So it's as if this test was meant just for this situation. The difficulty completely goes away, and now we're taking limit. N goes off to infinity of just n plus 1 to n plus 1. We have a tie in degree, so we take the coefficients where it's highlighted. The resulting limit is 1/2. Then just consult our oracle here of all the summary for tests on stuff. If you're dealing with the root test and we get something less than 1, then we have information on absolute convergence on this one. So we're in that nice situation. We'll say less than 1 because that part now tells us summation AN converges absolutely. And that was pretty fast. Usually after we do announcements and our first problem in the class, we're beyond 740. So this is a pretty fast problem just because we zeroed in at the right test we should use to start. We tried ratio test on this. It's probably not going to be so nice. I'm not saying it's impossible, but you could imagine it'd be a bit of a nightmare with the algebra because you would have AN plus 1 divided by AN. There's just way more stuff. Here, it's kept simplified, compact all the way through, and so the limit was easy to calculate. Well, it's nice to look into the root test one more time. It does come up in the homework sets here and there, but we mentioned a couple times, the ratio test is kind of the superstar. It's the one that gets used the most often, so we used it the most on these notes as well. So now we're turning over to power series finally, the next section. Here's where things feel quite a bit different out of nowhere. In power series, the reason we call it a power series is because of that feature right there on the red dot. There's now x to a power inside the series itself. It's definitely kind of weird. Notice the indexing is at 0. It's not a requirement, but it starts to get more and more common closer we get to Taylor's series and the Maclaurin series. So we'll refer to the CNs, Cn here multiplying Xn, manifested as C0, C1, C2, all the way down the line, as just being the coefficients of the power series. The coefficients are a big determination on whether this thing is going to converge or diverge. But what we're really trying to do with all of this is think of this as just another honest mathematical function. We'll often even use function notation and write out f of x represents the total sum of this series when it actually converges. And so it's equal to C0 plus C1 all the way down the line. We'll say that the domain of the set, the domain of f is the set of all x for which the power series will converge on. But really there's two kind of concepts here. When we say the set of all x, we're referring to an interval I of convergence. So I is going to be written in as something like this. It's a set that could be AB, or it could be AB like that, or it could be AB like that, or it could be AB like that. Weird, right? It's an interval for sure, but what we don't know about the interval is it open on both ends? Does it diverge on the boundaries A and B? Or does it converge on one boundary value A, but not the other? Or B, but not the other as well? Or it could converge on both boundary values. The ratio test is going to help us with some of that, but it never helps on the boundary values. That's the weird thing about these kind of problems. So the set of all X represented this way, and all this is the domain of F. We refer to it as I, interval of convergence. And so we're now thinking of this as being an honest to goodness mathematical function, depends on X, and its domain is interval of convergence, which is influenced heavily by what were the coefficients in the very first place. If there are large numbers, we might not converge on a large set. We might converge on just one number. But if we had something like maybe divide by 1 factorial, divide by 2 factorial, divide by 3 factorial, convergence is almost a guarantee. And the interval I might be the entire real number line. So that's what's going on so far with power series. Our goal is to work with these carefully to see all the moving parts. And the first big part is the center. Every power series has a center. This one's centered right at A. This one is centered right at 0. Let's mention here, centered at A. This one's harder to see, right? Because it didn't right in the center. Well, if that's the case, it's just automatically implying the center is 0 on this one. Let's write it in by saying it this way. The sum from 0 to infinity of Cn x power of n is equivalent as a sum from 0 to infinity, coefficient Cn times x minus 0 to power of n. And that seems like a silly thing to do, but now it exhibits what the center is. This one is centered at A is 0. Just easier to see there. A is 0 is the center on that one. So that's the first concept of the power series. The center is a really important concept because that's the one point you're guaranteed to converge on for a value of X. You'll always converge at the center for sure. So we're just getting started. Here's two kinds of power series, centered at 0, centered at A. Later on, we might call this one a Maclaurin series and this one a Taylor series, just because of how they're centered is the only difference between those concepts. And here's a particular one. This is a famous function. This is the world's first example of a function that is continuous on its entire domain, all real numbers, but it's differentiable nowhere. At every single point, despite the continuity at every point, we've lost differentiability. Excuse me. It's a weird function that has some restrictions. A is between 0 and 1. B has to be larger than 7, and it has to be an odd integer. Weird. And look at the summation. It sums from 0 to infinity, a power of n cosine bn pi times x. Well, that means the Weierstrass function is not exactly a power series. It's very similar in nature, but to make it an honest power series, the x you see right there has to be on the outside raised to power n. It's on the inside, and it's the coefficient b that's being raised to power of n. But this part right here, the fact we're doing a summation from 0 to infinity, that's the similar bit. And this is such an important function in analysis. This is a good one to take a look into as well. So this one's a hard one to plot because software cannot go up to infinity, but this one does converge. So if you sum from 0 to say 100, you get a really good view of the Weierstrass function. Let's take a look at it, and someone's implemented this in Desmos. not me. I found this on the internet. Here's the Weierstrass function. Takes a minute because it actually has to work on plotting this thing. It is a fractal, good eye on that. If we take that part right there, this is kind of hard to show, but if we took that part and we really zoomed in on that really closely, everything's broken down here. But if we had the tools to make this work, that's what you would see emerging just again. At any point, if I zoom in, the whole pattern just seems to repeat over and over again. Maybe you've seen, say, like the Mandelbrot set on YouTube, infinite zoom ins on fractal patterns. This is one of those functions, really pretty weird. Zooming in on this in Desmo's not so easy to really show what's going on, but let's attempt it anyways. It's got to reconfigure or replot the points. It's trying. You can see it kind of update there. And just keep zooming in on this level. And you can kind of see some instabilities coming in here, but the structure just keeps on coming back. Software through Desmos is still like 10 years behind. To really show this well, you'd have to code this up yourself. Using something like Python could do really well, efficiently show this fractal behavior. But that's a bizarre function. Anything that's dealing with power series or is similar to a power series like this one has those kind of oddities going on. So we're starting to think of power series, including an X, as being honest functions. And it's really widening our understanding of what a function even is. This one was so weird that it challenged a lot of strong-held beliefs in the mathematical community. This was a wild counterexample that essentially rewrote mathematics correctly once it came out. So that's our work. We're working with power series. This one is just a weird one. Any questions about that Weierstrass function? Okay, you can use this again to play a little bit more, changing the values of A around and the values of B around on it to see how it updates. It's really the same kind of curve, but the features of how high the peaks go, those kind of things are just modified by those values. So coming up next, here's another good example. Let's make this go on the next page. This one is an honest power series. Not like the Weierstrass function where X was never raised to a power. This time it is. We have a real power series on this one. These are the things we're going to now regard as functions. And if that's going to be the function, the very first thing we want to know is, what is its domain in the very first place? Starting thing would just be finding out where it's guaranteed to converge. So to get there, let's expand the power series. Let's call this f of x equals summation an, just to refer to it's this, the original power series here. We're writing down the first 4 terms. This gets a little bit weird. That's why we're putting in some extra space. Indexing starts at 0, so the very first term is x minus 3 power 0 over 0 factorial. We've mentioned this before, but 0 factorial is defined to be 1. That's helpful for us that it was defined in that way. If you take combinatorics, there's some arguments of why it's a reasonable definition in the very first place, but it helps out in this definition, right? We didn't divide by 0 at index 0. 0 factorial is just a 1. Then might as well put down a couple more. 1 factorial is 1. 2 factorial is 2 times 1. And so on down the line, like we've discussed. So that's our very first term. Index updates to a 1. So we get plus x minus 3 power 1, 1 factorial, and just rinse and repeat. We're going for 4 terms, so x minus 3 squared, 2 factorial, x minus 4 squared, over 3 factorial, and there's our first 4 terms. Let's maybe simplify it just a bit since, sorry, say again? I did. That was really weird. I must have been thinking a couple thoughts simultaneously. Thanks for fixing that one. That should have been at x minus 3 squared. The 3 should just carry in each and every time. So now in simplification phase, x minus 3 power 0 is a 1. But if you recoiled at that, I would understand. We're going to come back to that 1 right there. because there's another convention, much like this one, that only comes in this particular chapter in mathematics. Ordinarily, we say this. If we're not in the context of dealing with series, power series, Taylor series, and Maclaurin series, we would always say that 0 to the power of 0, undefined. Well, let's test this out. Not every piece of software agrees on that statement. Let's see what Desmos says. 0, power 0, 1 according to Desmos. That's awfully weird. Let's check out a different calculator. TI-84 calculator is a pretty trustworthy system. I might have done this once already. Yeah, that's what last thing I used on the TI-83. Go 0, power 0. TI-83 is telling you immediately undefined. And it has very good reasons of saying so. Calculus 3 actually gives us those reasons. The trouble is, you could regard x, or use this 0 as a variable x, that 0 as a variable y, and there's lots of ways you can head to 0. It doesn't always come out as a 1. Like Desmos is saying, undefined domain error is probably the more accurate way to say this. But in this context, we're going the Desmos route on this section in this book. 0 power 0 will be regarded as a literal 1. So that's a little bit weird, but what it allows us to do is start the summation at 0, not write a one-term exception and say summation 1 from infinity. Here's the exceptional term that just doesn't fit in because of 0 power 0. We're getting the same stuff. We're just allowed to now write this compactly. It's much like allowing 0 factorial to be 1. We didn't divide by 0 in the first term, so we can write all as just a summation without 2 terms or 1 term as an exception. So that's the idea. On this one, we'll have plus x minus 3. And just finishing these out, x minus 3 over 2, x minus 3 over 6, and so on. Any questions at all, folks, working on part A? Okay, now here's the interesting question for part B. We don't know its interval of convergence, but we'll always know one specific value that's guaranteed to converge on. Anyone see what it must converge on for x? Yeah, absolutely. Just imagine you plugged 3 here, and all down the line, or you did it up in here. Plug 3 into there, we would get a 0, but that's convergence. So let's write it out this way. It ties in with the center, which we can find by taking the opposite of whatever the number is right there. Center equals a, which is equal to 3, which implies f of 3 is going to be 0. And so the power series converges on its center. But again, we have a convention that we have to write in. Ordinarily, 0 power 0 is undefined, but we'll say here, by convention, in chapter 11, 0 to the 0 power is defined to be a literal 1, as weird as that sounds. Well, that's the rundown with this power series and some of the odd elements that we're going to see in chapter 11. 0 factorial is weird, but there's reasonable ideas for why that's an acceptable value. This is much weirder, in my opinion, but if we allow 0 power 0 equals 1, we can write down our power series as compactly as possible is the main motivation behind that. But any last questions at all, folks, with our example 2? Oh, hang on. Yeah, the f of 3 should have been 1. Sorry about that. I should have been getting zeros on those, but 1 right there. Thanks for spotting that value. Let me control Z that part. F of 3 should have been 1. I was getting excited with those zeros there. Let's maybe just write in here just for emphasis. F of 3 should have been the 1 that we highlighted in 0. plus 3 minus 3 plus 3 minus 3 squared over 2 plus 3 minus 3. Looks like I forgot a power on that. 0, 1, 2. That should have been a power 3. Power 3. Power 3 on that one, divide by 6. And so on down the line. But then, just like you said, only the 1 survives. Through that convention, 0 power 0 is 1. Does that make better sense with those corrections put in? Okay, so that's our interesting generic power series. One thing that we might start talking about as we see it, though, is that factorial down below is almost a giveaway. We still have to show this because results can be pretty surprising, but a factorial down below tells us the domain / interval of convergence is large. Possibly, more likely, the entire real number line is where this is going to converge on. So that's saying pick any x you'd like, something to a power of n just can't outpeak a factorial. This one is likely to converge, almost as a guarantee. But that's what we're doing next. I'm actually finding the domain / interval of convergence, and another related concept, the radius of convergence as well. So that takes us down to this concept. This is our big theorem in this section. Everything else was just definitions saying what's going on with our new concept of a power series. And now here's this random power series once again. You have two concepts that we're really interested in. R is going to be radius of convergence. I is going to be the interval of convergence. And there's only 3 things that can happen. So here's our trichotomy that comes up. No matter what you specify for coefficient Cn, either you have case 1, the series converged only on its center. If that's the case, we'll call the radius of convergence 0. The interval of convergence isn't even an interval to set containing one number, just the center. We were guaranteed to converge there, but if that's the only number we converge on, that's what we indicate R and I. It's a function with a domain element being exactly one number, making it not a very interesting case at all. We want to avoid case 1. But that's the center for the related concept. And it came from taking that value there, excluding the negative sign. The next nice case, like the problem we were just looking at with the factorial of the denominator, is that the series just always converges. Doesn't matter what x is, we have convergence. When that happens, we'll say the interval is the entire real number line, so negative infinity to infinity. Because that has infinite length, we say the radius is infinity as well. And then here's case 3. Case 3 is the annoying case. This one requires testing beyond the ratio test. And essentially every power series we're looking into, we're using the ratio test, perhaps the root test if the format just looks right for it. But in case 3, if we find that the series converges on a set like this, x minus a less than r, diverges when it's greater than r will be the radius of convergence, and the interval will be of this form right here. Notice it's based off the center. It's guaranteed to converge on the center. The radius is just telling you how far can you go to the left, a minus r, how far can you go to the right, a plus r, to still converge. Our interval could be an open set, a half open set like we discussed, this one or this one, or a fully closed set. But every single one of them is based off the center. That's a good thing to just tie in. Let's also discuss why is there further testing on this? That's kind of a tricky concept as well. It's all about one small issue with the ratio test. Notice it says convergence of x minus a is less than r. Well, they're talking about this case. We're going to make it come out less than 1 for convergence. Greater than r, divergence. We're talking about this case. but there was no case to talk about equals 1. This is where the ratio test fails. It fails on the boundary values, and that's where we're going to have to use the other tests like these above. Or perhaps a harmonic series or alternating harmonic series comes up. If those happen to be in the problem, we'll just state them and their known convergence or divergence. So lots going on here. As we run through these problems, I'll also indicate what case are we in, so we can think about that as well as we analyze the problems. Because knowing what case you're in massively determines how much work you're going to do on this, case 3 being the big one. There's actually big hints on the homework set as well. 11.8 says 3, 5, 9, 21 are 10 points each. That's because it's a case 3 problem. There's further testing on those. These are 5 points each, but that's because they're either case 1 or case 2. Those are fast problems. You just use the ratio test, you state your conclusions, and then it's done. So let's give this all a try. Once I decide on the screenshot, let's go here so we can consult this as we go. Starting with that power series there. X to the n divided by n times 3 power n. This one's weird. It doesn't have a factorial in the denominator. That means it probably is case 3, requiring further testing. But the best way to know what's going to go on with this one is, let's give it a name. Summation an is now named. Let's state the test we're about to use. The work for the ratio test involves the nth term, highlighted in blue, also involves the n plus 1th term. We'll write as in green, just like we did in the last section. We bump the power n by 1, so this is xn plus 1. Down below, and replaced by n plus 1 everywhere, so n plus 1 here, and 3n plus 1 here. So that's the next component in the ratio test. Then we do a limit as n goes to infinity of absolute value an plus 1 divided by an. So same structure in the statement of the ratio test. But one comment we should make right here, because it can be confusing with the last section. The last section, we often looked into the role of what is absolute value doing. And sometimes when we use the ratio test or the root test, we said, well, it has to be right here, but the next step we can drop it because the terms are positive. All of that logic goes away the moment it's a power series, because now x can be positive or negative. Absolute value is just a required feature of this kind of problem. So let's mention it here. We must use absolute value on that step. And we'll see why as we go. On the very next step, we're just substituting in the information. This is limit n to infinity. Following the color coding, heart and green, we're just throwing in that value. Let's factor it a bit as we go. Xn plus 1 is x times x power n. N plus 1 we can leave just as it is. But let's also factor 3 power n plus 1 in the same way. This is times 3 power of n. Multiply now by reciprocal of an. We're dividing by it to get n 3 power of n, x power of n. Now the ratio test is pretty much running right at that step. It's just about done, really. We want to do our fast cancellations. 3 power of n is gone. X power of n is gone. And now n plus 1, n, these are positive quantities as n goes off to infinity. Absolute value bars pass through anything indexed by n, but not x. Absolute value is going to center right on x itself. So this is the reason absolute value bars must be here. They coalesce right on x here. So it turns into a limit as n goes to infinity. The limit looks weird at first, but there's a bit of a trick on here. It seems kind of confusing just by visual inspection. First thing we put in is absolute value of x from that part. This n survived. And down below, we can distribute 3 in if we'd like to get 3n plus 3. But look at how the limit is indexed. It's indexed by n. That means every single thing not involving n is constant. So x is a constant in this limiting process. You don't have to move it outside, but sometimes that helps to see. So let's write in this as a quick comment as well. If we're indexed by n on the limit, then absolute value of x is constant with respect to lim as n goes to infinity. That's kind of a weird thing to put in. That's just a limit structure, but I just wanted to highlight n is no way involving absolute value of x. They have nothing to do with each other. So here's a nice limit law from Calculus 1. You can take anything that's regarded as a constant, even x on this thing. Let's maybe do it on the next line down though. And you can move it right in front of the limit. It's not a required step, but honestly, anything you can do to make the limit just easier to visually process, it's worth that extra effort. Now the limit is clearly just a rational function, tie in the degree, numerator and denominator, like seems to happen a lot as we mentioned. Limit on this one is just the 1/3, grabbing coefficients. So absolute value of x times 1/3 is the result. Now, when we use the ratio test, this has never happened, not once until this section. You can't make a conclusion here. The conclusion would depend on the value of x, right? If x is 2, this is 2/3. And then if we go to the ratio test, 2/3 as a limit is less than 1, and we have convergence. But we're doing something totally different here. We're going to say if this is bigger than 1 in absolute value, we have divergence. So instead, we'll focus on the convergence and say, through the ratio test, less than 1 is conditioned on convergence. And we just solve for the x's that meet that condition on convergence. So let's say it this way. Take the absolute value of x times 1/3, grab a pen, and immediately say less than 1. We say that because this part is condition for convergence in ratio test. And the goal on this problem was find the radius of convergence, interval convergence. We might as well force convergence right here into the problem. But we have one issue though. Sure, we know convergence when the limit's less than 1. We automatically know divergence when the limit's greater than 1. We don't have to solve that part. But we have to worry about that part. The test failed when it's exactly 1. That happens when x is 3 or -3. Value of 3 or -3 here gives a limit exactly 1. Ratio test is inconclusive. So we work backwards. If we don't know what the series is, we'll test it as some new series. So really weird logic, right? It's very different from what we did in the prior section 11.6. We still are using the ratio test, but force in that condition. So once we do that, we can say, continuing on, absolute value of x is going to be less than 3. All I've done is clear the denominator. This has given us one important value already. If absolute value of x is less than 3, then this tells us radius of convergence itself is 3. We want both the radius and the interval, so that's half the information. And at the moment, it's like a number line. Here is the entire real number line. We have the center of this. Let's take another look. Centered at 0. Let's make that a comment as well. That's pretty important. Centered at a equals 0. If it looked like, say, that one, this one would have been centered at positive 4/5. 5 there affects the center as well. It's kind of an annoying one. But if it looks something like this, just x to a power, center is automatically at 0 for this one. So we'll place the center right down here. If we said the radius of convergence is 3, it's like a radius in a literal but one-dimensional sense. Imagine this is like your circle, go right 3. I have no clue if we converge or diverge there, so we'll just put an open circle for the moment and then resolve it later on. But we can also go left 3. we for sure have convergence between. That's what the ratio test was all about. If absolute value of x is less than 3, convergence through the actual ratio test itself. So we're converging there. The open question is, what about the boundary values? Boundary values require further testing. So that means for this particular problem, it really is a case 3 problem. The radius is finite. It's 3. Whenever that happens, we are losing a lot of information on the boundary values. So we're about to start that further testing on this one. Any questions so far before we go to that next step? Okay, so these problems are a little bit long when that happens. Think of this as really, it's now 3 problems. First problem was use the ratio test. The second problem is find out what happens at -3. Third problem, find out what happens at +3. And it's all based off this here, the original power series. So let's carry that down just as an easy reference. And here's the next step. Test at x equals -3. Let's just start there. At -3, the thing that we named as summation an now is written as summation n goes from 1 to infinity. We're doing a literal substitution, just plugging in 3 right in there for x. Or excuse me, -3 is plugging in for x. So this is now -3 power of n divided by n times 3 power of n. This is an odd looking series, but it actually simplifies a whole bunch. -3 power of n divided by 3 power of n. Can be rewritten as -3/3 power of n, which means it's just -1 power of n. This is really an alternating series right at -3. So now it's equal to summation n from 1 to infinity, -1 power of n divided by n. So now it's an alternating series, but this one actually has a name. Anyone recall what this one's called? Exactly. It's convergent and the alternating harmonic series. Correct. So let's call this is the convergent alternating. I'll just simplify that down to alt harmonic series. That's a fast statement. So that's probably exactly what I would do if I saw this right here. You could test it with the alternating series test, but same exact conclusion, more writing. So go for the easy way. That's definitely heavily encouraged. The moment you spot a name series, just state the outcome and the name. So at -3, converges. We can solidify that now. The last open question is, what happens at +3? We can figure that out. We'll have our entire answer to this thing. So a little bit more space. Next, we're testing at x is +3. At +3, summation an is now n1 to infinity, summation. +3 goes right exactly there inside x as the power in the power series. So 3 power of n times 3 power of n. But this one's even easier to analyze, right? I honestly think this one's tricky if you feel a little rusty on exponents because of this trickiness right over here. But this one's just a full-on cancellation. So we get summation 1 to infinity, 1 over n. Now, this one is the divergent harmonic series, and you can say that in right here. But if you think about the number of things you write down, you might just say P series, P equals 1 diverging. That's maybe slightly less work depending on how you write it. But let's say that this is the divergent harmonic series. So our further testing really wasn't that wild. We just plug in the boundary values, simplify the power series, look at the outcome, and sometimes it really is just as fast as this. Other times we'll see one problem like it. There really is some extra work that you have to do here. Maybe p-series, geometric series. Usually stuff like comparison tests never comes up. You'd have to work hard to make the problem nasty for that. But at this stage, all we now need to say is our conclusions. So let's say it down below. And let's write it a slightly different way. You don't have to write it out this way, but the reminder of what we're doing here is we're thinking of the power series as an honest mathematical function. So you might state your conclusion this way, f of x, which is equal to, let's write it in this way to really emphasize it's a power series. F of x is defined to be from n equals 1 to infinity, x power of n times 3 power of n. And I still have to remind you, if you feel like that's a weird function, look into how you define sine and cosine in trigonometry. I promise you it feels weirder. This is at least a formula, right? With lots of terms, but not as weird as a process. This has interval of convergence. The main thing to write in is I. It's what we refer to as interval of convergence. It's bracket -3, 3 parenthesis. We lose convergence right on the right boundary. Kind of weird, right? And radius of convergence. Radius of convergence is just how far do you have to leave the center till you hit one boundary or the other. Doesn't matter if you converged or diverged on that boundary. The distance is 3, so the radius is 3 itself. Well, that's the conclusion on this one, folks. This is our full analysis of a power series. So what did we do, really? We wrote down something weird mathematically, some kind of analytic function. But when we ran it through all of our testing, we found this is the domain of f. Kind of interesting. For every value of f in this domain, this is almost an ordinary function like you would expect. Except there is one problem here. The convergence is absolute on the inside of this domain, but the harmonic series is conditionally convergent. So it's actually weak convergence on the very left point to -3. That could cause some problems if we're thinking of this as an honest mathematical function. Because if you look into conditional convergence, last page in section 11.6, it questions what you really mean by sum to that function. You could do some weird rearrangements of this and have it converge to a different number. That means the function does not give a unique output right at -3 if you give this a rearrangement. There's a lot of extra things going on here. If you think of it as a domain, it still kind of fits that picture, but be suspicious even on the bracket value -3. Look into how it converged, and you might change your mind and call that a parenthesis in reality. But that's the end of what we would have to do for this problem. The last bit is just a reminder, we're working on honest functions, and that's what we're going to culminate with in section 11.10. But that's how case 3 goes. We need a break after that one. So here is a case 1 or 2 problem next. Any last questions at all, folks? Ending on this analysis? Okay, so next one is n factorial times x power of n. If you look into that, I mean, really look into what's going on with this, we can say, yeah, the center is at 0. It will converge on its center, but pick x equals 1. If x is 1, it turns into that. And there's no way that converges. If you're adding together factorials, factorial alone gets rapidly very large. That's automatically divergent. This will allow it to converge, but only at one point on the center. So that's what I would think about when I eyeball this one. We still have to show all the steps that support that, but having a set of expectations before you launch into the problem is pretty valuable, I'd say. So we're probably in case 1. Radius is 0, interval of convergence would be the center, also 0. Let's see if that really happens. Let's start by saying, use the ratio test. forgot to give this a name, so let's just put it in right here quickly. Call the original thing summation an. Grab the next term. That would be n plus 1 factorial times x power n plus 1. So standard way, we go to the n plus 1 term, just change the n there. Then the ratio test involves a limit. As n goes to infinity of an plus 1 over an. So now let's just drop in our values. Limit as n goes to infinity of n plus 1 involves n plus 1 factorial, but we could factor it as n plus 1 times n factorial. Factor x as well, x times x power n. So standard steps we've been taking all along. This one had no denominator, so it's much easier to put the limit together. Now divide by n factorial times x power of n. And here's our immediate cancellations. This is gone, x power of n is gone. Absolute value centers right on x. That's the only position it lands on. N plus 1 is always positive. So I'll leave absolute value of x on the outside, like we did in the last problem. And we take the limit as n goes to infinity of n plus 1. So that's what happens on the ratio test. But in the ratio test, this limit, well, it depends, right? We can't necessarily put down a value on that limit. It depends on x. Most likely you'd want to say, what value would you pick if you weren't so worried on x? In other words, if it looked like this, sorry, say again. Yeah, that would just be a limit of infinity altogether. So now let's bring x back into the picture. The output really just depends. It's either positive infinity, and this is if x is not equal to 0. But the limit is different if x is 0. If x is 0, the limit is 0, because 0 is going to just multiply n plus 1 altogether here. Well, it would do it right here as well. Or if x was 0, you just are summing a whole bunch of zeros altogether. Well, there'd also be a 1. Don't forget that part. The 0 power 0 is 1. But however, down here in the limit itself is 0 if x is 0 itself. Looking into this a little bit further, this has a center a equals 0, which is why it's giving us a value of 0 right there. So let's take another look into our summary for the ratio test. So if x is set to 0, if it's set literally to the center value, then on the summary for tests, we have a limit following this. The limit is 0, it's less than 1, absolute convergence. But absolute convergence is not so exciting because we have 1 and then a whole bunch of zeros for all the terms of this. So it looks like this power series is just kind of a nonsensical thing altogether. But here's what we can say. If x equals 0, the limit is 0, and this is convergence. So converges only at x is 0. And a foregone conclusion now is that radius of convergence is length 0. That's because the interval of convergence is 0 again, just the center. So if we put it on a number line, here's what it looks like. We converge there at 0. That's why the radius of convergence is 0. You can't budge any distance left or right, or infinity takes over on this limit and it just diverges immediately. So this one is the weird one, the one that doesn't really fit as a function whatsoever, unless you're not too worried about a constant function. It's a pretty boring one. So that's kind of nice in a way, though. It's totally done right at that step. We like case 1, case 2 problems because the conclusions are so rapid, but we have to handle case 3 problems like the one above when they occur as well. Any questions at all, folks, on finalizing this one? Okay, let's try another one then. Again, if you're thinking back in algebra, literally all we're doing using calculus is trying to come up with What is the domain of that function? That's the whole idea here. This one sadly is definitely case 3, and you can almost tell. Denominator is n cubed, and it does grow fast, but its growth rate might not be fast enough if you pick x to be a large enough value, because we're raising this to a power n. Domain can't be too big here, but it's more than just the center for sure. By the way, the center on this is hard to configure. Let's analyze it this way. So if we want to look into the center of this, 5 plays a role as well on this thing. So we would take 5x minus 4 to the nth power, visualize factoring out a 5. That would give you 5 power n, x minus 4/5 power n if we factored it out. And then that would tell us center, which we often write in as a, is positive 4/5. We can also see it from here. We would take the opposite sign, take the positive 4, divide by any coefficient you happen to see here. If it was a 7, center is at 4/7. This is just the algebra that would support that as an idea. So that 4 and that 5 reconvene in that same way as a pattern each and every time. Well, now we know the center, it's guaranteed to converge at 4/5. Our goal is essentially to do this. Place down 4/5 right here, because that's a known point of convergence. And we want to know how far to the left can you go and how far to the right can you go to still converge. To get there, we'll call this a summation an. Let me write it in blue so I don't mess up the color coding. An is 5x minus 4 power of n divided by n cubed. An plus 1, hopefully my voice holds out for the rest of this, is going to be 5x minus 4 power of n plus 1, n plus 1 power 3. So those are the two pieces we need in the ratio test. Let's now apply it fully by taking limit n goes to infinity, an plus 1. Let me change colors on that. An plus 1 is in green. Divide by bn is giving us a limit that goes n heads towards infinity. An plus 1 is this structure, but let's factor it down just a bit for ease of cancellation. 5x minus 4 times 5x minus 4 to the nth power. Then divide it by n plus 1 cubed, we can leave in that format. We can still take the limit even if we didn't expand it. Multiply by the reciprocal of this one, n cubed, 5x minus 4, power n. And ratio test always starts off kind of ugly for these kind of problems, but just keep at it, keep chipping away at it because they simplify fast. This 5x power 4, 5x minus 4 power of n rather, cancels immediately. Well, that's the only cancellation, but n cubed divided by n plus 1 cubed is a pretty fast limit to take. So now this time, absolute value settles on the 5x minus 4. This turns into absolute value, 5x minus 4 times the limit as n goes to infinity of n cubed divided by n plus 1 cubed. We can get this limit resolved. Our job is, well, not quite done, but we're nearly done with the ratio test at least. Anyone see by visual inspection what this limit really should be? Yeah. Absolutely. The numerator is n cubed. And if you expand this out, it is a good amount of work. It's not too bad. It's a direct way. The very first term you get when you expand that is n cubed again. So it's n cubed over n cubed for the most dominating terms. And that means the limit on that is exactly as you said, just a 1. This is 5x minus 4 multiplied by a 1 over 1. Where indicated in yellow, it came from the coefficient 1 here, and coefficient 1 here, where this would turn into n cubed upon expansion. So it's just 5x minus 4. And remember, what we do with that next is kind of interesting logic. We are putting in this directly in order to solve for all the x's, which would satisfy the convergence condition. So go less than 1 immediately. it helps to say this again. So let's in fact say it again. This is the condition for convergence. Now let's start working with this. If we have 5x minus 4 less than 1 in absolute value, then it would imply -1 less than 5x minus 4 less than +1. Much like when we had absolute value of x is less than 3. Now -3 less than x less than +3. Whatever number's here, we just split up in that kind of way. Then this allows us to start solving things. Add 4 to both sides. 3 less 5x is less than 5. Divide all 3 sides by 5 now, and we get that 3/5 is less than x is less than 1, or 5/5. So we're just about there. Right in the middle on our number line is the center. The ratio test says we have guaranteed absolute convergence if we move to the left up to 3/5. So here's 4/5. Here's 3/5. We put an open circle there because this is a point to resolve whether it will converge or diverge. Then move the same distance to the right, move 1/5 to the right, so we're at 5/5, or just a 1, if you prefer. And already this gives us the radius as well. You could actually spot the radius. If you have a 1 here and a 5 there, the radius is automatically 1/5, but that's a confusing thing to say. The shift of +4, -4, anything like that doesn't affect the radius. It's the factor right there. But now it's easier to see. A distance from 3/5 to 4/5 is 1/5. That's automatically your radius. Let's write it out, write it in this way. This distance is r, which is 1/5. Does that make sense to folks on finding that radius there? Okay, you might put a bracket to say from 4/5 to 5/5, which is 1, also a radius of 1/5. We have guaranteed strong convergence, referred to as absolute convergence in that range. So now we test boundary values. Anything can happen at 3/5, anything can happen at 1. So here's the further testing. Test at x is 3/5. So if we're going to run that test, we need to go back up to the top, grab the original power series, and just plug in that value. So at x is 3/5, we'll have that summation an is now a sum. This one starts at 1, going to infinity. Plugging 3/5 in here kind of makes sense in a way, right? We would get 5 times 3/5 minus 4 power of n, but that's just going to be 1 to the power of n. Their work looks like it's kind of just done at that step. So this is divided by n cubed, and we have a summation from 1 to infinity. The 5's cancel, 3 minus 4, and I said that incorrectly. It's -1 power of n divided by n cubed. So now it's really up to us how we'd like to test this. Either alternating series would work, absolute convergence test would work, really up to you. Any volunteers for a direction to go on this one? Good call. We haven't really used that much. So this is a kind of a fun one. It's come up, but we've never used it directly. So now we are. Absolute convergence test says, if this converges absolutely, it converges. So let's run this test. Really our first direct use of absolute convergence test, I believe. Absolute convergence test. There's an exclamation mark. We take summation absolute value of an, but we're still in the scope. X is 3/5. That means we're taking absolute value of this one. It's going to be a sum from 1 to infinity of just a 1 over n cubed. This is kind of funny in a way. Once you use the absolute convergence test, you're not done. Now it's a p-series. After we wiped out the negative sign, our power is 3 greater than 1, so we have a convergent conclusion on that. So now it's P series. P is 3, greater than 1 is conditioned on convergence. So this implies summation AN converges. Back to the test of absolute convergence, where to go? We just showed the series converges absolutely. There it is, summation AN in absolute value converging. That means the original thing is, oh, hang on, the original thing is convergent. Doesn't help to go on the wrong line there. When they say then it's convergent, they're talking about that one here. So we'll say, therefore, summation AN converges. It converges by the absolute convergence test, but also you have to test it again through P series once you hit it with absolute value. So convergence here means we have, in fact, absolute convergence on the boundary. Not like the last time where it was conditional convergence. The function makes sense as a literal number when we plug in 3/5. We still don't know what that is. We'd have to find the sum, but there is an exact sum there. So that's testing on one boundary value, but I'm noticing we're not done, right? We have to test again. Let's see, how are we on time? Let's give it a try. We're testing at a boundary value 1. Test at x equals 1. What happens at x equals 1? We're just plugging 1 right here. So we get summation AN. It's a sum, n goes from 1 to infinity. 1 there is just 5 minus 4, 1 power of n. That's just 1 over n cubed. So much like we had a P series, P bigger than 1, and converging, same thing happened here and here. So we can just say this is a convergent P series. It's also absolutely convergent, just like on the last one. So absolute convergence right here as well. Our job is done. We can say radius is 1/5, interval of convergence, bracket 3/5, comma 1 with a bracket. And convergence makes sense at every point on this. So pretty interesting power series this time. Just kind of messy to work with. Any last questions, folks, before we call it a day officially? I guess the emphasis on that last problem is, even though we had a minute and a half, the further testing really is pretty fast because things simplify nicely. And the series you get are not like the ones with the comparison tests. They're usually a lot more direct to get a conclusion on. Well, we'll come back, finish off the last problem on here on Thursday, and then take a look into function representations. Thank you. Have a great afternoon, folks. See you all next class. Sure.
For number 19, do we want to include these values or do we just say the 2n?
We do have to include them, yeah. This one's kind of a tricky one if you want to
Because
see
I
a
thought
hint
it
on
was
how
like
it should
it
go.
was, I thought it was like n factorial.
It sort of is, but it skips. N factorial goes 3 times 2 times
But-
1. This one's descending by 2, or let me take a look. It's increasing by 2, yeah. So it's like a stronger factorial now in that one.
So would it be 2n factorial or just
It's a whole nother animal pretty much. It's not even a factorial in the original sense.
oh really?
Yeah,
I have
so
no
we would
idea
need
how
like a
we
new
use it.
symbol. Let me show you how I went against that one. This is which section again?
This is 11.6. Is this the like double factorial one where it skips every other?
Essentially 11.6 number this one.
Mm-hmm.
So when you go to put in the first part using the ratio test, it looks like this.
Okay.
So here's the n plus 1. And then you get n plus 1, let's see, yeah, n plus 1 n factorial. Flip it around. And even though this is a weird animal to handle, there's huge cancellations on it just immediately.
Oh, really?
Yeah, it's because the
Oh.
ratio test flips it around. Now you just cancel all down the line. saving the 2 times n plus 1.
Mhm. I did not know that. Okay, that makes more sense.
Yeah, it's a nasty one to even start, but it's actually pretty not too bad once you run through it.
Okay, that makes more sense.
Awesome.
Thank you.
Yep, you betcha.